Good morning, everyone. I'm excited to welcome you to our presentation today. We'll be exploring wastewater coagulation and flocculation. This is a crucial part of transforming contaminated water into clean, reusable resources through advanced particle removal technology. Over the next few slides, we'll cover how these processes work, their importance, and the benefits they bring to water treatment. Let's get started. Let's talk about why coagulation and flocculation are so important in water treatment. First, they play a crucial role in improving water clarity. By removing suspended solids and reducing turbidity, these processes help make the water clearer and more visually appealing. This is not just about looks. They're essential for ensuring the water is safe to use. Next, coagulation and flocculation are critical treatment steps, especially when dealing with industrial and domestic wastewater. They prepare the water for subsequent filtration and sedimentation, making those steps much more effective. Finally, these processes enable us to remove tiny particles that wouldn't settle naturally. This includes colloids and emulsified oils, things that are microscopic, but can cause problems if not properly removed. Overall, coagulation and flocculation are foundational to producing clean, safe water. Let's start by looking at the science behind coagulation. The first key point is particle repulsion. In water, suspended particles tend to carry negative charges. This causes them to repel each other, which actually helps keep them evenly dispersed and stable in suspension. Next, we have charge neutralization. To destabilize these particles and encourage them to come together, we add positively charged chemicals called coagulants. These chemicals neutralize the negative charges on the particles, reducing the repulsion between them. Once the charges are neutralized, the particles can start sticking together more easily. This leads to the formation of tiny clumps known as microflocs, which are too small to see with the naked eye, but are a crucial step in the coagulation process. Finally, rapid mixing is essential. By quickly and thoroughly mixing the water, we ensure the coagulants are evenly distributed. This high-energy mixing promotes effective charge neutralization and helps the microflocs form more efficiently throughout the water. All of these steps work together to remove impurities and clarify the water, which is at the heart of the coagulation process. Now, let's take a closer look at the flocculation process. Gentle stirring is key here. It encourages microflocs to collide and bond, forming larger visible flocs known as pinflocs and macroflocs that are much easier to remove from water. This process is crucial because larger flocs settle faster and are more effectively filtered out. Adding polymers, or coagulant aids, plays a significant role as well. These substances strengthen the flocs, which dramatically increases the speed at which they settle and improves the overall efficiency of filtration. However, controlling the mixing energy is essential. If the stirring is too vigorous, it can break fragile flocs apart, undoing the process. On the other hand, if the mixing is too gentle, it might not promote enough bonding and growth of the flocs. Typically, the contact time for this process ranges from 15 to 60 minutes. This window allows sufficient time for the flocs to form and grow, ensuring optimal removal of contaminants. So, in summary, effective flocculation relies on gentle, controlled mixing, the strategic use of polymers, and appropriate contact time to build bigger, stronger flocs for easier and more efficient water treatment. Let's take a closer look at the different types of coagulants we use in water treatment, starting with organic versus inorganic options. Organic coagulants, such as polyamines, PolyDADMACs, and tannins, primarily work through charge neutralization. This means they help neutralize the charges on particles in water, causing them to come together and form flocs. One of the key advantages of organic coagulants is that they produce significantly less sludge volume compared to inorganic options. This can make sludge handling and disposal easier and less costly. Another important point is that organic coagulants don't affect the pH levels of the treated water, which can be beneficial depending on your treatment process. However, they tend to be more expensive upfront, but this is often offset by lower disposal expenses due to the reduced sludge volume. Now, on the other hand, we have inorganic coagulants like aluminum sulfate, commonly known as alum, and ferric chloride. These work through a mechanism called sweep floc, where they form chemical precipitates that enmesh particles, effectively removing them from the water. While inorganic coagulants generate more sludge, meaning you'll have a higher volume to dispose of, they are generally less expensive initially. But keep in mind, the handling and disposal costs for this sludge can add up. Ultimately, choosing between organic and inorganic coagulants depends on several factors: water quality, cost considerations, your facility's capacity to handle sludge, and your specific treatment goals. Understanding these differences helps in making an informed decision that aligns with your treatment needs and operational constraints. Let's take a closer look at particle sizes and the challenges they present during treatment. Particles larger than 100 micrometers, for example, tend to settle naturally without much intervention, which makes them relatively easier to remove. However, when we move into the 10 to 100 micrometer range, things become a bit more complicated. These smaller particles can cause turbidity, making water appear cloudy, and they usually require coagulation processes to be effectively removed. Now, when we're dealing with particles smaller than 10 micrometers, specifically colloids, they're highly stable because of their charge. This stability means they resist settling and require specialized coagulation treatments to be removed efficiently. An important concept here is zeta potential, which measures the strength of the particle charge. If the zeta potential is near zero, particles tend to settle easily because they're less stable. But if the zeta potential has a high magnitude, the particles are more stable in suspension, and we need to apply treatment to destabilize them. Understanding these size ranges and the charge stability helps us tailor our treatment strategies effectively, ensuring cleaner water and more efficient processes overall. Let's now turn our attention to some key operational considerations and how we can optimize them for better water treatment. First, dose determination is crucial. We often rely on jar tests, which are standard, but for more precise control, advanced tools like streaming current detectors can be used. These help us fine-tune the coagulant dose by accurately measuring charge neutralization, ensuring we add just the right amount. Next, there's the concept of dosing balance. It's a delicate act. If we overdose, we waste chemicals and create more sludge, which means additional handling and disposal costs. On the other hand, underdosing leaves particles suspended in the water, reducing clarity and treatment efficiency. Striking the right balance is vital for optimal performance. Water chemistry also plays a significant role. Factors like pH, temperature, and overall water composition can dramatically influence how well coagulation works. Understanding these parameters allows us to adjust our processes accordingly, ensuring the treatment is as effective as possible. Finally, expert operation is fundamental. Skilled operators who understand the nuances of the process, combined with properly designed equipment, such as rapid mix and slow mix chambers, are essential for successful treatment. Proper operation and equipment design work hand in hand to produce the clean, safe water we aim for. All these considerations connect back to our overall goal: optimizing treatment efficiency while minimizing costs and environmental impact. Now, let's take a look at some real-world applications and the benefits they bring. First, municipal wastewater treatment plants. These are critical in managing urban water and ensuring safe water reuse. Our technology plays a key role here by improving treatment efficiency. Moving on to oil refineries, where hazardous sludge can be a major challenge. Our solutions help reduce that sludge, making the process safer and more environmentally friendly. Paint detackification systems are another important area. They help in removing paint residues from wastewater, which is essential for compliance and environmental protection. Industrial effluent treatment facilities also benefit greatly, as they need reliable methods to treat complex waste streams effectively. Now, looking at the major benefits, our solutions enhance downstream filtration and sedimentation, which means cleaner water and easier removal of solids. This ultimately reduces operational costs because processes become more efficient and less resource-intensive. Plus, our technology significantly improves water reuse potential, helping industries and municipalities conserve this vital resource. Importantly, it removes organic matter, oils, and pathogens, key elements that safeguard public health and protect the environment. All of these processes are fundamental in ensuring that we meet environmental standards and support sustainable industrial and municipal operations worldwide. Now, let's look at the exciting innovations and future directions in water treatment. First, we have novel composite coagulants. These are advanced materials that combine different coagulant properties to enhance removal efficiency. We're also seeing hybrid processes that merge coagulation with oxidation or membrane filtration technologies, which can significantly improve overall water purification. Next, microscale testing is gaining importance. These miniaturized testing methods help us select the most effective coagulants and determine optimal dosages more accurately, especially tailored to specific water conditions. This means better performance with less waste and cost. Finally, there's a strong push toward eco-friendly solutions. Researchers are developing environmentally friendly coagulants that aim to reduce sludge volume, lower toxicity, and diminish the overall environmental footprint of water treatment processes. All of these innovations are aligned with our broader goal, making water treatment more efficient, sustainable, and adaptable to future challenges. Now, let's look at the final slide, which emphasizes the importance of coagulation and flocculation as the cornerstones of effective wastewater treatment. These processes are truly complementary. They work hand in hand to transform unstable, tiny suspended particles into larger, more stable flocks that can be easily removed from the water. It's really about creating a system where these particles can be aggregated efficiently, making the entire treatment process more effective. Moving on, we see the concept of optimization excellence. This means selecting the right chemicals, dosing them appropriately, and controlling mixing processes carefully. When we get these elements right, we not only maximize treatment efficiency, but also enhance sustainability, reducing chemical use and energy consumption, for example. Finally, the slide points to future innovation. The industry is continuously evolving, with ongoing innovations and expert operation playing a crucial role. These advancements are key to ensuring we produce cleaner water and foster safer environments worldwide. So, by focusing on these core processes and continually improving, we can meet the growing challenges of water treatment and make a meaningful impact globally.